Hey everybody, Dr. A here, and in this video we are going to provide an introduction with some background information on thin wall pressure vessels. So let's go ahead and get started. So commonly seen in industry are both spherical and cylindrical vessels that are supporting an internal pressure. And we see this a lot in chemical, mechanical, and industrial engineering purposes. So if a vessel, whether it be spherical or cylindrical, is supporting an internal pressure, let's call it P, we must ensure that the stresses that develop in its shell do not exceed an allowable stress. Otherwise, you could have a failure of the vessel. So to analyze these vessels, the first thing you want to investigate is if the vessel is considered thin or thick. So for the purposes of this video, we're only going to talk about thin wall pressure vessels. So a vessel is considered thin if its inner radius to wall thickness ratio is 10 or more. So we can say R sub I divided by T is greater than or equal to 10. Okay, so that would be whether it's spherical or cylindrical. If you have this inner radius to wall thickness ratio greater than or equal to 10, it's considered a thin vessel. All right, so let's talk about each of these two common types of vessels, the spherical vessel and the cylindrical vessel. So let's start with spherical vessels. Spherical vessels. So a spherical vessel looks basically like a ball, okay? It's like a three-dimensional circle, okay? Spherical vessels are typically primarily subject to what is called longitudinal or axial stress due to the internal pressure that is developed. So let's make a note of that. We're going to say subject to longitudinal or axial stress due to internal pressure P. All right. So this is the longitudinal stress, or you could call it axial stress that is acting in the cross section of the shell. Okay. So let's say we have a spherical vessel, and I look at a cross section of that spherical vessel. Okay. That's a horrible diagram. Let me try to redraw that. It's a little bit better. Okay, and of course we have this inner radius R sub I, and we have a wall thickness T. And if we're dealing with a thin vessel, which that's what we are talking about in this video, we have R sub I over T is greater than or equal to 10. So the longitudinal, or otherwise called axial stress, is the stress that is developed in this shell that's coming in and out of the screen at you. So I'm drawing these little dots because this is representing like a stress field coming in and out of this annular 2D sketch for you. Now I could try to draw this in 3D, but I would do a horrible job drawing it in 3D, so I'm not even going to try that. The internal pressure that we're speaking of, that we're talking about, is all on the inside, okay? So you have this internal pressure that's all on the inside, pushing on the inner surface of this pressure vessel, and that's that internal pressure P. So the stress that we calculate is going to be called sigma sub L for longitudinal stress. And that's going to be equal to P times R sub I, which is the inner radius, divided by 2 times the wall thickness. Okay? So that's how we calculate that longitudinal, or otherwise called axial stress, in a spherical vessel. What about cylindrical vessels? Let's summarize that here. So we're going to say cylindrical vessels. So cylindrical vessels are subject to two types of stresses. One of them is the longitudinal or axial stress, just like the spherical vessel. So we're going to write that down again. We're going to say subject to longitudinal or axial stress, just like the spherical vessel. And so that's actually going to be calculated the same way as we saw with the spherical vessel, and that's going to be internal pressure times the inner radius divided by 2 times the wall thickness. But not only are spherical vessels subject to longitudinal stresses in their shell thickness, but they're also subject to what are called circumferential or hoop stresses, okay? So I'm going to say also subject to circumferential or hoop stress, okay? And I'm going to call that sigma sub h for hoop stress. So the hoop stress, it turns out, is just going to be the internal pressure times the inner radius divided by T. So it actually turns out that hoop stress is equal to 2 times longitudinal stress. Okay, so that's it in a nutshell. That's the basic way to investigate spherical and cylindrical thin wall pressure vessels. So in the next video, we're going to do a numerical example where we look into this with some actual numbers. So if you found this video helpful, please hit like and subscribe.